everyone, and welcome back to episode 3 of this series. In this episode, we're going to tackle a more involved dynamics problem, and toward the end, we'll even bring in some kinematics. So let's get right into it. What we have here is a slide following the equation y equals 1 over x, and our goal is to figure out how much acceleration we can expect a mass to experience as it goes down this slide. The first thing to remember is what we derived in episode 1. The gravitational force acting on a mass on an inclined plane of inclined theta is mg sine theta. For every point on our 1 over x slide, we can think of the mass as being on an inclined plane with the same slope as the instantaneous slope of the slide. As the mass moves, the incline of the plane changes, and so does the gravitational force acting on the mass. Because we're looking to find the acceleration as a function of where the mass is on the slide, it would be useful to express the force acting on it in terms of x, rather than the angle of an arbitrary inclined plane. We can do this by evaluating sine theta in terms of x1 when the mass is at any point on the slide x1, y1. To do this, let's let our generic incline extend to the x-axis, meeting it at x2. Sine theta, by definition, equals the height of the incline over the hypotenuse, which is the square root of the height squared plus the length squared. We already know y1 in terms of x1, but we need to use the slope of the incline to find x2 in terms of x1 as well. To do this, we take the derivative of the slide when x equals x1, and we can call that y1 prime. We then write out the equation of the incline using two-point form, ignore y2 because it equals 0, and solve for x2. Now we can substitute for x2, take the common factor of y1 squared out of the square root, and cancel it with the y1 in the numerator. We can do this because y1 is always positive, so it will equal the root of its square. Next, we can differentiate the equation of our slide and plug in an x1 term for y1 prime, which gives us sine theta in terms of x1, and thus the gravitational force acting on the mass in terms of x1, the x-coordinate of the mass. Now, most slides I've been on have at least some amount of friction, so let's find the total force acting on the mass, assuming friction is present. We know that the magnitude of the force equals the coefficient of friction times the normal force. We also know that the angle between the vertical and the perpendicular to any inclined plane of inclined theta is also theta, which lets us separate the components of the gravitational force just like we did in episode 1. But this time, we're looking for the perpendicular component, Fg cosine theta. This is because the normal force will perfectly counteract this perpendicular component, since the mass moves perfectly along the instantaneous incline, meaning that the normal force equals minus mg cosine theta. This should look familiar. We have the friction force in terms of the incline of an arbitrary plane, but we want it in terms of x1. So we follow the same procedure as when finding the gravitational force, except we use cosine theta instead of sine theta. Our diagram hasn't changed, so our x2 is still the same. After substituting for x2, canceling out the common factor of y1 from the numerator and the denominator, and substituting for y1 prime, we find that cosine theta equals x squared over the square root of 1 plus x to the fourth, letting us define the friction force and find the net force acting on the mass in terms of its x-coordinate on the slide. mg minus the coefficient of friction times mgx squared all over the square root of 1 plus x to the fourth. Now that we've solved for the net force, it's simple to determine the acceleration the mass experiences as it goes down the slide, which lets us explore the kinematics of this slide. The particular question we will be answering asks for the final velocity of the mass after it has fallen from one point at x0 to another point at x1. Recalling one of our kinematics equations, the final velocity squared equals the initial velocity squared plus twice the acceleration times the distance traveled. To make matters simpler, let's assume that the initial velocity is 0 and that the mass can overcome the static friction. The complication here is that we don't have a value for acceleration. It's constantly changing. What we're really looking for is twice this acceleration times this small distance plus twice the next acceleration times the next small distance, etc. all the way down the slide. Letting the small distances approach 0 and summing infinitely many terms is called integration, which is exactly how we will approach the solution to this problem. From one point at x0 to another at x1, we want to integrate twice the acceleration times the infinitesimal distance traveled along the slide, which we will call ds. Because the bounds of the integral are in terms of x, but traveling along the slide isn't strictly motion along the x-axis, we will have to make some substitutions. For any ds traveled down the slide, there's an infinitesimal dx component and an infinitesimal dy component. This means that ds squared equals dx squared plus dy squared, and ds equals the negative square root of dx squared plus dy squared. We use the negative because we let going up the slide be the positive direction when we applied our inclined plane method. Factoring dx out of the square root, we get ds equals minus dx times the square root of 1 plus dy dx squared. By differentiating 1 over x, we know that dy dx equals minus x to the power of minus 2. So ds equals minus dx times the square root of 1 plus x to the minus 4. We rewrite our original integral, factoring out the 2 and the g from the acceleration term, separating the numerator of the acceleration term from the denominator, and substituting in our new definition for ds. Notice that in this term, multiplying the top by x squared would make the numerator equivalent to the denominator, simplifying the fraction to minus 1 over x squared. Factoring out a minus sign and distributing this fraction, we get our final integral with bounds and differential both in terms of x. Minus 2g times the integral from x0 to x1, x to the minus 2, minus the coefficient of friction, all multiplied by dx. We can split the integral in two and evaluate each separately. The integral of x to the minus 2 is minus x to the minus 1. We evaluate this at x1 and subtract its value at x0. The integral of a constant is that constant times x. We evaluate this at x1 and subtract its value at x0. We plug these back into our expression for the square of the final velocity, and take the negative square root, since going down the slide is going in the negative direction, and we have our answer. Giving a starting and ending position, we can now predict what velocity the mass will end up going. If we were to slide a mass from the point where x equals 0.5 to where x equals 1, for example, and let the coefficient of kinetic friction arbitrarily be 0.4, we find that the final velocity is minus 4 meters per second, where the minus sign indicates that the mass is going down and to the right at the angle of the instantaneous slope at x equals 1. To see how much friction slows down the mass, we could pretend that the coefficient of friction were 0, which would give us a final velocity of minus 4.4 meters per second. Still minus 4 to the correct precision, but you get the idea. So that's pretty much it for this episode, guys. I hope you enjoyed it, because it was a lot of fun to make. If you want to see me make any more videos or have any other thoughts, feel free to let me know in the comments below, and I will see you all next time.